conceptually, but we hadn't dived into the code by the end of Monday. By the end of Wednesday, we'd gone through all the code with that. Any questions? Anything that you're running into? Okay. Yeah.
For func app node,
Uh-huh.
the first piece
Right.
is a what?
Arithmetic expression. So yeah, sorry, I didn't write the grammar on the board. So the first part is syntactically, it's arithmetic expression. So it's just simply, with the lights down, can you still see when I write on the board? Okay. So it's just simply, you asked about the app node, right? Not the def node? Okay. Syntactically, it's this. Semantically, though, this had better evaluate to a function, and then this would be the argument to that function when you call it. So there's a lot of ways this could evaluate to a function. It could be a lambda expression, which would directly create an anonymous function that you're going to call. It could be a variable reference, which is bound to a function. We're actually going to use that a little bit today. It could be a variable reference, like I said, it's bound to a function. And then when you semantically evaluate this expression, you look up the variable, you get its value. Its value is a closure, right, a function, and then you apply that closure here. Does that make sense? Or this could itself be another function call to something that happens to return a function. However it gets there, as long as this evaluates to a function, then you call that function in essence. We walk through the code of applying this function to this variable.
We're going to have to check if it is a function.
So one of the semantic checks, and this is mentioned in the assignment, you have to make sure it is a function. Also because, sorry, this is in the base one we give you. This is what the new one is going to look like. And so this had better be a function. The other thing that you're going to have to check semantically is that the number of arguments passed is the same as the number of formal parameters expected by the function when it's declared. But that's nothing more than is the length of this list equal to the length of that list. So we give you the base abstract syntax for it, where it just has the two. You will need to modify the abstract syntax nodes. I think the easiest way is, you know, this has to be here. So I would still store a single, I think fun expression was the name of the field. And where it had before arg expression, I would do something like arg expressions and make that a list of AE, or array of AE, I guess, would be the simplest way. Does that make sense? So if this comes in as, so this is, once it's lexed, this is going to be a list. This is going to be, right, suppose that this comes in when you're parsing. This is your expression. Then that is the first thing in the expression. And this is simply that. Does that make sense? That would be how I would approach it. And then you actually have stored this list. And then at runtime, what you would do is simply evaluate this to get the closure, make sure it is a closure. One by one, evaluate each of these recursively, just with recursive calls to calc. And then, I mean, you know how to sort of apply something to every element of something here. Well, sorry. Even beforehand, you could just make sure that the length of this array was equal to the length of the formals that were stored with this closure. Does that make sense?
So when we're finished, we can make delete by not node handling, because this will handle that.
No,
same.
binop nodes, that's totally separate. That's for binary operations. This is for function. You're only going to be so you're grafting in the binop stuff from the last lab and making it work with the fact that we now have return values or ret vals. But the other changes are only in width function definition and function application. So this doesn't replace the binop nodes, or did I misunderstand?
Okay, an example of a binop node would be parenthesis plus 1, 2.
Right.
And then this, it says the first thing is a function,
Right.
plus is a function, and then it has a number of parameters.
But
1 and 2 are parameters.
we still have the case in here in the grammar that, so notice we've sort of made it plus a hard-coded kind of keyword, if you will, that's going to be checked by the parser. That all is still the same, all the binop stuff. One way you could do this, by the way, this is not what you're doing for the lab, but if you think about what Racket actually does, remember I said this could be the name of a variable that happens to evaluate to a function? You could pre-populate what we've been building as, remember I said we could take the empty environment, we could pre-populate it with a whole bunch of predefined things, like pi and e and stuff. You could also pre-populate it with a variable called plus, right? And plus would internally be bound to a closure that performs plus operations. So you can basically cause it to do that kind of stuff. There's a little bit more to it than that, but we're not doing that. Plus, minus, times, divide, mod, that's all hard-coded in, and that still collapses to a binop. This will be for user-defined functions only. Okay. Good question, good clarification. Any other questions about the lab? Okay, let me point out one thing. Some of you may have noticed this. In class, I had, for widths, I had used the following clause. Actually, let me give myself some more room here. So in class, I'd used this grammar for the width. The CI2 interpreter that was distributed with the notes and everything through content in the section of Learning Suite, that also used it parsed according to this grammar. The CI3 interpreter, though, we used to actually just do this. Because if there's only one, why have the extra set of parentheses? So, but this is purely a parsing issue. Once you actually create the node, you still have these three pieces, and so the calc part didn't change. So you'll notice the parser, so I made the change in the CI2 to the way I wanted to start doing it now, and I forgot to make the change in CI3. So some of you may have noticed the parser that we give you for a width will actually be parsing this. Whereas what I had done in class was this. It doesn't matter because you've got to change it to ultimately be that. Okay? So if you want to, if you find it helpful, you could go to the CI2 interpreter that we give you, copy just the one else if clause for a width node, and just replace what's already there with the width. That at least has the notion of extract one binding and then extract these two pieces out of it. It really, either way works. Again, you're going to have to ultimately change it to that for the assignment. Okay. So some of you might have noticed that slight discrepancy between CI2 and CI3. But again, it's a discrepancy in a part that you have to be changing anyway. Does that make sense? Questions about that?
Just
Yeah.
clarify that's in CI2 where we can get that?
Yeah, so CI2 has that, whereas CI3 left out these parens. Okay. So if you want to, just go to CI2 and copy and paste that.
But then we'll still need to change it regardless.
But then you'll still need to change it regardless. So in the end, it really doesn't matter which base you start with. I just wanted to correct or clarify this in case it was causing anybody some confusion. Any other questions with the lab? Okay, now I know it's not due for another week, and you've already had a bit of time to work on it. The feedback I've gotten from students in the past is that the level of understanding with this one is a bit more than than it was for this first lab. This is probably the biggest lab you've had so far. That's part of why you're given extra time. So treat this as one of those assignments in the mirror are closer than they appear kind of things. And I definitely would try to get started with it as soon as possible. Again, the extent of the changes is not, is part of it's finding in what you're, grafting in what you're doing, part of it's thinking through the parser, part of it's thinking through the semantic parts of it. The big part I hope is that will take your time is pushing you to understand the interpreter we've already built and the way it's using environments, and we're going to talk about that a little bit more today. And then hopefully after that, the amount of changes is not, again, this is not thousands and thousands of lines of code kind of an assignment. Also, I know I emphasized last time this with the parser, but going back to the semantic errors, we try to enumerate them in the lab. But another good way to think of that is just simply, okay, semantically, so look at the assumptions built into what we're doing, right? Semantically, so if you look at this is the CI3 interpreter with this change, by the way, grafted in. So again, this is the cleaned up version. When I've said this many times before, when I code live in class, I'll make up variable names on the fly, and it may not be the same as the cleaned up. Also, this is a little cleaner in terms of formatting for the 3 parameters passed to the extended environment. But you'll notice that we calculate the function expression, and then we start trying to get fields from it as if it's a closure. Well, there's an assumption. This had better be a closure, semantically. And then we bind formal to actual, which is fine because we only have one. That's a fair assumption now. But now that you're extending it to multiple parameters, those two had better be the same, the lengths of those lists, and so on. So just think about, as you're thinking about the semantics of an operation, okay, we're applying a function, better make sure it's a function. We're binding formals to actuals, better make sure they're the same number, and so on. You see the idea? Okay. Any other questions about the lab? Yeah?
When we're taking in symbols, do we want to throw errors if they're with or?
Yes, actually, that's a good catch. That is one thing that is in the assignment that I didn't actually mention when I was giving the over. Access denied. Okay, well, get to the right. There is a part right here on this line that I didn't actually mention when I was sort of giving the high-level overview of class, or in class. So good catch on this. One of the other things that you need to do is, since we now have the ability to define variables, you need to make sure that those variables are not part of these reserved keywords: plus, minus, times, divide, mod, colats. I think that's, oh, and also if, zero, and with, and lambda. Okay. Does that make sense? Because otherwise, otherwise you could have the ability to create a user-defined function called plus, and the only way to try to call it would be this. This is kind of getting back to the clarification you were asking about. The only way to call that would be this, but it would parse as this. Everybody see why? And so this is why, this is very common. Languages will have reserved keywords. You've encountered this before. Certain things you can't name variables, simply because it conflicts with the keywords in the language in a way that ultimately confuses parsing. Now this part's easy though. This is just when there's a width. Remember so there's two ways that you're actually trying to define where variables get defined or bound in environments. Okay. It's in a width expression or in the function call. So if we go back to the call right here, when we build a call to extended environment, we have a formal parameter here that's being about an actual parameter. You need to make sure that this formal parameter, or in the case of this lab, each of the formal parameters is not in some list of reserved keywords. Okay. Does that make sense? And there's a lot of ways you could do it. You could stick it in right here. You could stick it in with the width. You could put you could create your own function that's a wrapper around an extended environment that did that kind of a check. And then everywhere where you're extending the environment, it just automatically does it. So I could make instead of directly calling extended environment, I could call a make new environment helper function, right, that does this checking and takes the same parameters and ultimately calls extended environment. So again, multiple different ways you can try to code that. Is that clear for everybody with that part? Okay. Am I spending too much time on the lab? Because I really want to make sure going into the weekend that your questions are answered. At this point, like I said, Wednesday we had everything for the lab, and now we're going to start actually opening up some space between what we're covering and the next due date. And so that gives us some flexibility to spend the time that we need to now on the lab. Questions? Yeah.
So I'm not entirely sure I understand the difference between the funcdef node and the funcapp node.
Okay. Just think of it as, so thinking about it in C++.
Okay.
There's a certain syntax for defining a function,
Mhm.
and there's a certain syntax for calling a function.
Okay.
That's all these two are.
Oh.
So funcdef node, actually I think we have the grammar here, so I can just use this here. So this is the multi-parameter function. So this one is a function definition,
Got
a
it.
lambda expression. This is calling or applying a user-defined function.
Okay.
And so this is parses as a function definition node,
Mhm.
or fundef or funcdef node for short. This is a function application node. In other words, when you hear application, just think function call. Okay. A function application node, and that's a funapp. Yeah.
Okay, and then, oh wait, were you calling them something?
No, go ahead.
Oh, okay.
Yeah.
The other thing I was really confused about is how to make a function variable arity.
You don't have to for this.
We don't have to for this?
No.
When it has
the syntax says, I can make a function with one formal parameter, I can make it with a function with two, a function with three, but that particular function has fixed arity.
Okay.
In other words, I can make fixed arity functions of any arity the user wants to declare.
Oh, but as long as they have in fact declared it.
Yes. So for example, so yeah, here's just an editor. Let me make this bigger here. So what it means is a user could do something like that to create a two-parameter function. They could do something like this. Sorry, this editor is matching parens form. Something like this to make a three-parameter function. But each of those functions has fixed arity.
Okay.
Okay. So all we're saying is in the grammar over here, the grammar will allow you to define a function of any fixed arity.
Mm-hmm.
But it's different than a variable arity function.
Okay. makes sense.
And then likewise, because you can have any arbitrary, and by the way, this could be 0 because Cleany star is 0 or more. So you could write a parameterless function, right? And you've written those before in different languages, including Racket. And since I have the ability now to have some arbitrary number of parameters, again, not variable arity, but syntactically I can declare a function to have as many parameters as I choose to in the language. As the programmer in the target language, you have to have the ability to have multiple parameter function calls. Questions on this? Anything else? Okay, so what I'd actually like to do to start into the idea for today's material is to walk through an example with diagrams of exactly the data structures, the environments and closures that are created for a simple function, create a function, give it a name, and then call it by that name. And what we're going to get to, hopefully time permitting, is we're going to see that there's a little gotcha if you try to do that with a recursive function. All right, so let's go back to the code here. This is, again, the cleaned up CI3 interpreter. By the way, I was mentioning before class, so it's useful. I've been going through, let's run the lexer, let's run the parser, let's run calc. That's fine if we're sort of developing it and you want to see it step by step. Let's just look at, we'll just run the whole sequence on particular input strings. And so there's the interp function that does that for you. There's also, if you haven't seen it yet, there's an interp-f function that we also give you. And interp, so here's interp and interp-f. Interp-f, you give it a file name as a string, and that way you can put a whole bunch of tests or a more complicated example in a file, and just say run that file. All right, so let's interpret the following. Let's use with to give a function, so we're going to define with to give a name to an anonymous function. So in other words, with f being the result of, sorry, we don't have the parens around there in this version. You're putting them in since you'll have more than one parameter. Sorry, just trying to match up parentheses here. Okay. All right. So this example that I just fed in looks like, sorry, where did I set that? Let me write this with better formatting. So with f being defined to be the following function. So in other words, this makes and returns a function that takes one parameter, and when called, adds one to that parameter and returns that result. We're going to take that anonymous function, we'll use with to bind a name to it. So this function is now named f, or more precisely, the identifier f is now bound to this function. And then within the body of the with, we're going to call that function. Okay? And so when I run that, and I pass 5 to f, which adds 1 to its input, I get back 6. So let's look at the data structures that are created with this. So when we first feed this into the interpreter, we'll call calc with that parsed expression. And remember, we're passing in as the environment in which to evaluate that. We're going to pass in the empty environment. So one way of thinking of this is, in the beginning, there was nothing, right? So in the beginning, there's this empty environment. And I'm going to use just some notation. This is not formal or anything. I'm just going to write here next to it expressions that we're evaluating in that environment. So this whole width is going to be evaluated in that environment. Everybody understand the way I'm drawing it? Okay. So now we get into calc, we evaluate the width. Okay. So with a width expression, think back to the code, or even pull it up if you have your laptop handy. What's the first thing that we do with a width expression? So if we're calculating this, what's the first thing we do? Yeah.
You compute the second parameter.
Right. This initialization expression,
Yes.
right, we're going to, initialization, or I think in the code binding expression, we're going to evaluate this first in the current environment. So we're going to evaluate lambda, this lambda expression. We're going to evaluate that in this empty environment. What does evaluating that return? What is evaluating a function definition return? A closure. That's our internal representation for a function. So here's the closure. I'm just going to write closure rather than the whole closure val. And the closure has, remember, formal, body, and an environment that it extends. So what's the formal parameter for this example? X. What's the body? Yeah, we're going to add that. And then this is actually an abstract syntax tree for that hanging off of here. I'm just going to write it this way. And what environment does this extend? What environment are we creating it in? Yeah, the only one that's around. But more importantly, we're evaluating this lambda expression is being evaluated in this empty environment. So the closure that is built, let me actually label these things. The closure that's built remembers the environment in which that function was created. Right? For this simple example, it just happens to be the only one in town. Okay? All right, so now go back to the width. We've evaluated this recursively, and we've got a closure. Now what do you do with it? What does a width do? Should I bring back up the code, or you remember kind of the sequence of it? I can bring the code back up. I don't mean that as in a, don't make me have to bring up back the code. So we can do this. Let's just look at that. Sorry, maybe I should have done this to the side and not behind the whiteboard. So I went ahead while it was coming down and scrolled down to the width node part. So the first thing is evaluate this sort of binding expression, the initialization expression, I think is how or val expression or something. That's what I called it when I live coded. And the cleanup code is this binding val. So we've got that. So the binding expression is this lambda. We've evaluated that and got the binding val. That's our closure. What's the next thing? Pardon?
Get the symbol.
Yeah, we're going to get the symbol. That's F. And we're just simply going to bind it. Remember, the way we create variable bindings is in an environment, and environments extend other environments. So the symbol here is F. Binding val is the closure returned from this. And what environment is that going to extend? The one we're currently in. Remember, widths always extend the current environment. And again, there's still only one at this point. And then after that, we're going to evaluate the body of the function, the body of the this is the body of the width. We're going to evaluate that in the context of that new environment. So let's go through and do that. So we build a new environment. Or in our types, it's an extended environment. So what's the variable that, actually I'm gonna write this a little bit different. I'm not even gonna label it that way. I'm just gonna write the bindings within it. So we bind the formal parameter, or sorry, this symbol is what we're defining, right, with the width. So F is bound to that closure, and this environment extends that environment. Everybody understand the way I'm drawing it? So environment is just a lookup table. This variable has this value, and it extends this environment for all the things that aren't defined locally. So this is the environment that's built when we create that extended environment that binds the identifier F to the result of this lambda expression. So now we're ready to evaluate this expression, the body of the width, in the new environment created, the new local scope created by the width. So now we'll invite, and that body is F5. So we're going to evaluate that in this body. So now what happens? First off, what does that parse as? It's a function application, right? So function application, we evaluate this expression and we evaluate that expression, right? So let's do this one by one. Let's evaluate F. Well, let's evaluate this expression. What's the process? So what does that parse as? A symbol or variable reference. So what do we do when we calculate a variable reference? You look it up in the current environment. If it's not there, you just start following the chain. Well, fortunately, here it is. And it's that. So this F evaluates to that closure. 5 trivially evaluates to 5. That's a literal. So now we're applying this closure. So now that we have the function, the closure, and the actual parameter, now we're going to apply this closure, this function, to 5. Now what's the process? Yeah.
And then it just takes the closure and evaluates the body with that put in place of the formal parameter.
Yes, with the 5 put in place of the formal parameter. Now, there are some methods that actually do it through straight sort of substitution, and then there's a whole bunch of gotchas with keeping scope straight and stuff. And if you want to, you can read about, there's things called substitution models, and then you've got things called alpha reductions and beta reductions and all this other stuff. The way we're keeping that all straight is just with environments. So we'll simply build, so when you call a function, it creates a new local scoping block for the parameters of that function. So we have another environment that binds the formal parameter. Where do we get the formal parameter from? Pardon? Yeah, the function definition. So remember this F, so at this point it's all, regardless of how we got there, it's boiled down to a closure and a value, an actual parameter. So we look in the closure, get the formal parameter, that's X. And we bind that to the actual parameter, which is 5. Okay. Now here's the key question with this one. It's going to come up later when we get to recursion. What environment does that extend? To make static scoping work, what environment does that extend? environment of the closure. If we just do this, that's dynamic scoping. And that's what we said we didn't want to do. It always extends the environment of the closure, and pardon the awkward diagram here. Sorry, I'm going to write it this way. So that's the environment it extends. That's why, remember, sort of the environment closes around the function definition. So the closure remembers in static scoping, the environment is created. That way, by the way, if this happened to reference some free parameters that were defined up here earlier, they would still reference those instead of anything that happened to happen between this function definition and eventually calling it. Does everybody see why that environment extends the environment in the closure and not the caller's one? Okay. So now, what do we evaluate in that environment? So we've already bound the formal to the actual. Let's go back to what you were saying. What do we ultimately want to do with that function application? What's the last step?
Calculate the body.
Calculate the body, right? Where do we get the body? We look in the function definition, the closure. So there's the body. So we're now going to evaluate plus x1 in that environment. So what does that parse as? Okay, hopefully by this point that was one of those sort of slow pitch questions. Right, this is either a plus or a bin op, depending on how you do it, right? So you evaluate the two sub-expressions. Let's evaluate the x. What's the process there?
Look in your environment and see if you
Yeah,
find it.
this is a variable reference. Look in the environment in which we're evaluating this. Ah, there's x. So we found it. We don't have to keep climbing the chain. X is 5. 1 is just the numeric literal 1. I add those two together, and that produces 6. Do you see the process of all the data structures and the computation and calls that happens to get to turning this into the result 6? Yeah.
This might be a dumb question. Closure has an environment, right?
Yeah.
But the environment that is dx:5 extends an empty environment. How come it doesn't extend the environment that's in closure? Is it like a pointer, a reference? How do you describe that? Instead of like pointing to the environment in closure, you're pointing all the way back to the empty environment?
Yes, because that's where that closure was created. So if you think back to the example that I gave in Racket with sort of this f and g and these different versions of y, we wanted that y that was referenced in f to refer to the one that was in scope at the time that function was created. Even if later other things were created that actually referenced that variable. Right, so let's just suppose, hypothetically, suppose this wasn't an empty environment. This was the result of some other kind of computation farther up the line. Suppose this happened to reference y, and it had some value, or let's actually do it like the other example. It was 3. And suppose this wasn't x plus 1, but it happened to be x plus y. And suppose that also within this, since you can now define multiple things, or maybe it was nested, this one had this. So the question is, when you call this function f of 5, and it adds y to the obvious, so x is obviously 5, right? The form parameter is the actual. The question then is, when it encounters, so what would happen is this would now reference a y, right? So I look here, and it's not here. The question is, which one should I actually go to find that y? If I just did this one and looked here, I'm looking in the caller's scope, and that's dynamic scoping.
Okay, so I guess my question is,
Does that make sense?
nothing would ever reach back up several environments and change the value of y. If you're going to change the value of y, you make a new environment.
Yes, so that actually is a really, really important point. When we're talking about static versus dynamic scoping, I try to be somewhat careful with the language. Static scoping uses the environment that was in scope at the time the function was created. In other words, it's a scoping matter. It doesn't take a snapshot of all the values. So suppose suppose we introduced, and we're going to do this next week, the ability to change the values of things. Suppose we change this to, I don't know, some value. This call would actually reference that new value. So static scoping doesn't mean that you take snapshots of the actual values. It means that you remember the scope that you were in, not the actual current values of what's defined in that scope. Those values may change. So it's a scoping issue, it's not a state snapshot. Does everybody understand the distinction I'm making between those two? So did that help address your question?
Yeah.
Okay. All right. So let's work a slightly different example.